Okay, this is something we have already seen, a boundary layer in a furnace, right? In a reaction chamber. So this is a furnace, and then gas is flowing this end to the this end, and you develop a boundary layer, right, or stagnant layer, and this is the thickness of the boundary layer. Okay, so you have seen all these parameters, right? This is the what is the viscosity of the gas, the density, the velocity, and x is the distance along this direction, horizontal direction. So we had seen this thing, all these parameters in the context of the Reynolds number. Okay, so that was on a previous slide. So I don't think we need to discuss it in detail, because this was already discussed when we talked about thermal oxidation. Yeah? Okay. So this boundary layer considerations actually become very important in CVD, and for reasons that I've already mentioned in a previous lecture, that in an oxidation process, there are two fluxes that we were concerned about. So the oxidant flux through the boundary layer, right? And then the other was through the already grown oxide, and then you have a reaction flux. Okay. But in this case, the second component, that is the flux of the reactants through the already grown layer, is not important, because you are depositing on the top. Okay. So what becomes important would be the transport of the reactants through this boundary layer in the gas flow, and then actual reaction rate on the surface. So that is this part, and so the transport is by diffusion through the boundary layer. But also the other thing is that in this case you have reaction byproducts that should be transported back into the main flow through the boundary layer. So that is another factor. Now this is obvious: thicker the boundary layer, longer it takes for the reactants to diffuse to the wafer surface. Lower reactant flux arriving on the wafer surface would then lead to slower film growth if the growth is limited by the availability of reactants. Okay, so this mass transport is very critical, and that should be controlled. That is why you see all these different types of chambers and interesting constructions, because this is a very important parameter. So we'll just review this situation when an atmospheric pressure CVD reactor. Discuss that this is your wafer holder and the gas is flowing like this. Yeah. So we were discussing, or wondering why this wafer holder is actually tilted. Or in this barrel reactor, you have this wafers placed on a slanted surface. Okay. So what you are trying to do is to maintain a constant boundary layer, because if I have the thickness of the boundary layer changes, okay, as I proceed along the furnace, then I have a problem, at farther end of the furnace, right, the thickness is much more than at the beginning. So the reactants take more time to diffuse through towards the end of the furnace. Okay, so the flux will come down, and as a consequence, I would get a slower deposition towards the farther end of the furnace, if the transport through the boundary layer is the limiting parameter. So then that would lead to a variation from wafer to wafer, right? The thickness that you deposit would vary from wafer to wafer. So you can control this by actually, so if I want to fix this, and if I just look at this equation, so I can see that, okay, if I increase the velocity of the gas, right, then I should be able to balance out this factor, yeah, x. Okay, so x is increasing, the boundary layer is increasing, so I increase the velocity, and one easy way is to actually make the cross section through which the gas flows smaller. Yeah, so this is, you know, like you take a pipe and you're trying to pump water through it, and then as children you might have played with this pipe, right? You put your finger and then it goes farther. Yeah? Velocity increases, right? Same thing that is being done here, and exactly the same thing is done here. Okay, so you're trying to maintain a constant boundary layer thickness by these designs. Okay, so very nice thing. So you have an equation that describes what is going on in a fluid flowing through a pipe, right? And then we apply that to modify the design of a CVD chamber. Okay, so the deposition process is something that we have already seen, what happens on the surface, nucleation and so on and so forth. But you have this wafer placed on something, right? And you have a main gas flow, and this is your stagnant layer. Okay? So you can have various things happening here. So one is gas phase reaction. So the reactants could actually react or decompose in this, right? And then get transported to the surface. And then absorption of the film precursors on the surface, and there can be surface diffusion and surface reactions happening on the surface. And then some of these reactants may desorb from the surface. Okay? And we have discussed this nucleation of the particles of the film by their random movement. Okay? And then actually initially you'll have islands growing, so you can get nanoparticles, right? And then you get a closed film. Yeah? Now, very important is that the reaction byproducts should be removed from the surface. Okay? So they would, so most of this would be volatile at the process temperature, so they escape, okay, into the main flow, and then that would be carried away by the main gas flow. So what happens in a CVD reactor is something that can be very complicated to analyze. This is an example of a deposition of silicon on a silicon surface, okay? And in this particular case, it is doped p-type, so you're using phosphine, is mixed with silane, okay? So the different things can happen in this case. So this is silane, SiH4, decomposes to silylene, okay? Silylene, S-I-L-Y-L-E-N-E, S-I-L-Y-L-E-N-E, okay? Silylene, so this is also a gas, but this is very unstable, and hydrogen, okay? So this is a reversible reaction, and then you can have disilane formed by the reaction between silane and silylene, again a reversible reaction, okay? So you have this now 3 compounds, and the silane could be adsorbed on the surface. So this is adsorbed silane. Okay, you have also disilane, okay, adsorbed, and this is silylene, also adsorbed on the surface. So you have actually, there are 3 parallel paths, yeah, by which silicon can be deposited. Okay, but this is sequential, right? You see this? Yeah, this is sequential, and this is the other sequence. Okay, and then you have the adsorption of hydrogen onto the surface, and that should also go out. Essentially, you're trying to deposit silicon with trace amounts of phosphorus in it, right? So what remains would be the hydrogen. Okay? And something that we usually don't discuss in a CVD when you describe the CVD reaction is that you have a main gas flow and all these gases are coming in. Okay? A very small fraction, about 10%, is actually used in the deposition. 10 to 15%. The rest just flows out. Okay? And you can imagine that in VLS applications, we are talking about very high purity, 6, 7, 9 purity silicon and phosphine. So very expensive gases, they just goes out. Okay? So that has to be treated before you let it out into atmosphere. Now that's only a part of the story, but the silicon deposition by pyrolysis of silane is something that has been studied thoroughly because of the importance of the technology. Yeah? You are talking about silicon devices. So if you look at all semiconductor devices that are in use today, silicon has a very important, an overwhelming market share, if you would like to say so. Okay? Now, only recently with, the LEDs, things are looking slightly better for some of the other materials. So, as a consequence, the CVD deposition of silicon by pyrolysis of silane is one of the best or thoroughly studied technique, reaction. So, you can read this 27 contributing reactions have been identified out of 120 possible elementary reactions. This means we have only looked at 3 of them, right? It's very complex to analyze because of gas-phase reactions, and then you have adsorption on the surface, right? And then surface reactions that lead to the film deposition and desorption rates. Okay? So each of these could limit the reaction rate depending on which one is faster, which one is slower, and so on. Right? So it is quite complex. So most of the cases, what you do is you just take the whole deposition process as single reaction, right? Yeah, and the overall reaction is the only rate limiting thing. So you have 2 things. One is the mass transport, then some chemical reaction that is happening that leads to the film deposition. But we will see there some examples that I would discuss that could challenge this approach, and you may get different things during the deposition. So this is something that we have already discussed. So you may have sequential processes and parallel processes, right? We have seen that adsorption of silane, silylene, or disilane on the surface. These are all parallel reactions. Okay? On the other hand, the production of silylene by decomposition of silane is a sequential process, right? If you take that route, it would be coming like this. So then you get the film, and we have discussed how the overall reaction rate looks. So you have the serial limiting steps. So you have, so these are Arrhenius plots. Okay, you have also done worked out a problem in a quiz. So this is the overall reaction rate, right? Comes down like this. So whichever is slower decides the reaction rate, and parallel competing reactions you have whichever is faster decides the overall reaction rate. So in this particular context, you can actually say, okay, mass transport, surface reactions, and then you have this. So this is one serial process, okay? And then I can analyze and say, okay, in this particular case, this step may be the limiting factor. Okay, just as an example. So we had this parallel route, silane, disilane, or silylene adsorption on the surface. This can be the parallel components. Okay, so this is something you can quickly read. Transport of the reactant through the boundary layer to the wafer surface. So these are things that happen during the deposition. Adsorption of the reactants on the wafer surface. Re-emission of the adsorbed species back into the boundary layer, that can happen, right? Surface processes including decomposition reaction, surface migration and nucleation, desorption of byproducts from the surface to the boundary layer, and transport of the byproducts across the boundary layer into the main flow. So these are the things that can happen during the film deposition. So I can now classify them into, so this is your mass transport, and then you have your surface reactions, okay, and you have mass transport here also, that is the transport of the byproducts across the boundary layer into the main flow. Usually people assume that this is not rate limiting, okay, but we may review this assumption later on. So if you now look at the process, so similar analysis we have done for the oxidation, so it should be easier for you to understand. So you have this main flow, boundary layer, this is a substrate on which you want to deposit, okay. So Cg is the concentration of the molecules, reactants in the main gas flow, okay. So you have a diffusion across the boundary layer, and the concentration on the surface will be lower because the material is being consumed in the deposition process, okay. So you have a concentration gradient, so that is basically driving your diffusion process, and you can write down the flux, diffusion flux, and this is the fixed first law of diffusion. So you have the concentration gradient, which is approximately equal to the difference in the concentrations divided by the thickness of the boundary layer, okay. You have the diffusion coefficient here, and d by delta S is written as Hg. Hg is the mass transport coefficient, okay. So same equation, and so mass transfer coefficient Hg is the ratio of the diffusion coefficient and the boundary layer thickness, okay. So after the reactants get transported to the surface, there are surface reactions, right, and there will be a flux, and that is given by Ks into Cs. So this is the reaction flux will be proportional to the concentration of the reactants on the surface, and Ks is the surface reaction rate in centimeter per second. So this is just following what we had done for the oxidation process also, right. So you can see the slower of the two processes would decide the overall rate of reaction, and under steady state, okay, what would happen is these two fluxes should be equal, okay. So you can equate this, we know Fd, the diffusion flux and the reaction flux, and you can equate them. And now if you look at this equation, this is something that you can calculate. If you know the volume of the tube, the pressure, temperature, right, I can find out how many moles of this reactant is there using Cv is equal to nRT, and that gives me Cg, right. And Cs is actually difficult to find out because that depends on what is the reaction rate, okay. So what you do is you rewrite this equation and express Cs in terms of Cg, okay, and then use that in one of these equations, yeah. So then it is possible to write this flux, steady state flux, as this. So you have Cg, yeah, concentration of the reactants in the main gas flow, divided by 1 by Ks, the Ks is the reaction rate constant, and 1 by Hg. Hg is the mass transfer coefficient, Okay. So this is a simple thing, you can work it out yourself, how to get this. Okay. So this equation is there for us to interpret. And this is again, if you remember, we have done a similar thing. So this is essentially the rate of growth of the film. Okay. So what is the increase in the thickness of the film with time? So this is T prime. You have a increase in the film thickness with time. Okay. So that is given by this equation. You divide it by n. What is n? N is the number density of product atoms in the growing film. So this is something that we have done in the previous example also. Like you remember, we talked about the how many molecules of silicon dioxide is there in a unit volume, right? That is something that we have already done for the oxide growth. Similar thing here. So you can see this n would be so many atoms per centimeter cube for silicon, if I am trying to deposit silicon. Okay. So this is a useful equation. So you have this, the denominator, okay, is 1 by Ks plus 1 by Hg. Okay, now how do I interpret this? Anything like this? So if I take this factor, if I take this inverse relationships, right? What does it say about, so these are two processes, okay? These are two processes, and you are looking at the rate which is inversely proportional to, what does this mean actually? The rate of reaction, right? Meaning that it indicates the rate of reaction, and this is transfer rate. Okay, centimeter per second. Both are similar, right? So you are talking about how fast it is going to happen. Okay, but then if this is very small, yeah, Ks is very small, so the inverse of Ks is going to be very large. Okay, so this becomes negligible. Yeah. So you can see that the slower, so whenever you have this relationship, right, 1 by something plus 1 by something, the smaller or slower of the processes would dominate the overall. This is always the case, right? You might have seen this Matheson's rule, or the lifetimes of carriers, right? You have the 1 by tau is equal to 1 by tau radiation, 1 by tau SRH, and so on and so forth. Or 1 by mobility, overall mobility is equal to the phonon scattering mobility and things like that. So whatever is resulting in the smallest value actually would dominate the process. So this is typical of a serial thing. Yeah. So this can also be drawn in this way. So you have this Arrhenius plot, growth velocity, okay. So that is the T prime that we discussed on a previous slide, and if you plot it as a function 1 by T, so this is Arrhenius plot, right? And you can see that this is your Ks term, and that has a E minus Ea by Kt form, right? So as you decrease the temperature, yeah, because this is 1 by T axis, so as you go towards the right, the temperature decreases, the reaction rate decreases. Okay? And this is the Hg term, and suppose Hg is constant, so you have this term, so the net growth velocity would follow the lower of these two at any given temperature. Okay? Now you can see this thing, that if I want to operate towards the left, where the temperature is high, okay? For example, if I want to get a dense film, yeah, this is a consideration in some of the cases, so you should actually have sufficient surface mobility for the deposited particles on the surface. So I may want to do my process at high temperature, okay? But then I have to worry about a mass flow control process. Yeah. On the other hand, if I don't worry about this particular thing, I may actually go to a range where this temperature control. So just what I am doing, if I want to control the overall process by controlling the temperature, what this tells you is that do the process at low temperature, not at high temperature. Okay. If I do the process at high temperature, meaning I have no problem, the reaction can happen very fast if I am able to supply the reactants on the surface. Okay. So then the supply of the reactants on the surface becomes the limiting factor. Yeah. So that is what this says, right? As I go here, the reaction rate is increasing, okay? But then at some point, the supply of reactants is not able to catch up. Okay? So that is what this says. So that is why, if you remember, now go back to the discussions, some of these processes like epitaxial growth of silicon, right, that need high temperature. Okay. So there you tend to do if I want to epitaxially grow a thick film of silicon, the temperature has to be high, and then I am worrying about how to design my process chamber so that the mass flow is uniform. That is why I want to have a slanted surface on which I place my wafer. Yeah? The boundary layer thickness is constant throughout, so I would get wafer to wafer repeatability, yeah, in the process. Okay. So this is something we have already discussed. The thicker the boundary layer, the more time it takes for the reactants to diffuse through the thicker boundary layer. Now, how do I solve this problem? So what we are saying is that the mass transport can become a limiting factor. Okay, when if you do the process at high temperature, yeah, so the reaction is very fast, but then you are not able to supply the reactants, okay, at a rate exceeding the reaction rate. Okay. So one thing is to write this equation in this form, so you can find 1 by Hg is equal to delta S by D. So diffusivity and the boundary layer thickness. So we would really like to review and see how these can be modified. Okay. So what we said is that reaction is very fast. Okay. This is the limiting thing. So can I now increase the mass flow by some means? So I look at this equation for Hg. So you have d by delta S. Hg is equal to d by delta S. So if I now, what do I want? I want to increase Hg. So I should either increase d or decrease delta S. Okay. Now one way is that in a gas, diffusivity is inversely proportional to the pressure. What does it mean? Diffusion happens by random movement of the particles, right? And they would, why the movement is random? Why is the movement random? Mean free path, yeah, they collide. Okay, when two particles collide, they actually, their trajectories change. Okay, and when they go through this multiple interactions of this kind, you don't know in which direction they are going to move. So if I have too many collisions, then the diffusion process would be slower. Yeah, too low collisions, I can actually increase the D. What it means is that if I reduce the pressure, I can increase D. Hg will increase. Okay. Now, boundary layer thickness also increases, that you can find out from the previous equations, where you had mu into, what was the equation for the boundary layer thickness? Square root of mu into x by rho u. So, what happens when the pressure decreases? Any obvious parameter that would be influenced by a decrease in pressure? What about rho? Density. Yeah, when the pressure decreases, density would, if the volume is the same, density would decrease. Yeah, PV is equal to nRT. Yeah, volume is the same, temperature is the same. So, N should decrease. So, the density would decrease. So, which means that the boundary layer thickness would also, pressure decreases, density decreases, and delta is inversely proportional to the square root of the rho. So, you would have, or the pressure decreases, the rho decreases. So, this would also increase, will increase. Okay, delta is inversely proportional to the square root of pressure. That is what we are saying. Okay. So, you would have this also increasing, and as a consequence, I have, you may think that, okay, this is increasing, this is also increasing, but here it is a square root dependence. Okay. And diffusivity is directly, proportional to 1 by pressure. So, Hg would increase, that is what it means. Okay. So, as a consequence, overall the Hg would increase if you decrease the pressure. So, what happens then? I have this Hg term has been lifted up by decreasing the pressure. So, I can now go to higher temperature, okay, but still operate it under the reaction rate limited regime. Yeah, this is one way to do it, right. So, reduce the pressure. So, I can actually do the reaction at lower, meaning higher temperatures. So, this is, now if I am reducing the pressure, usually a low pressure CVD process. Okay. On the other hand, if you have high pressure, we are going to bring it down. Yeah. Okay. So, all this high temperature process, for example, diamond growth, if I want to do diamond CVD, I mentioned that you need to do the process at very high pressure, also at high temperature. So, that process would always be happening in a mass transfer controlled regime. Okay. Very high pressure, also high temperature, right. So, you will have to have a very good design for the transport, the chamber or the furnace has to be designed properly, so that you actually ensure uniform gas transport, reactant transport to the substrate surface. So, you can see in this case, here it looks much simpler. You have a cylindrical furnace, you have a boat that carries the wafers, okay, you place them here, and diffusion through the gap between the wafers can be increased by reducing the pressure. So, that is the idea, okay, in an LPCVD. So, that is why you are able to place the wafers very closely spaced. Now, one thing that you should remember is that as the gases, reactants enter and you have deposition here, right? Yeah. So, you have to make sure that the gas that is going in does not get depleted of the reactants by the time you reach the center of the wafer. Okay. So, there must be ways to look at this. For example, you can increase the spacing between the wafers, or you can actually retard the reaction by reducing temperature and so on and so forth. So, this is some way to get uniformity across the wafer in a vertical placement of the wafers like this. I will show you some examples. So, there are advantages of LPCVD. For example, one obvious advantage compared to APCVD, let's say, yeah. So, what can I change in an APCVD reactor? Pressure and the, temperature, okay. Of course, the reactor design can be changed, but once you design a reactor, there is not much you can change. Only the temperature and the gas flows can be changed, but it is still atmospheric pressure. So, but here you have two knobs to play with. One is the pressure and the other is the temperature. So, you can fine tune specific sub-reactions to obtain desirable properties. So, of course, you need to develop an understanding of how different things like the decomposition of the reactants, surface absorption, desorption and so on could be changing with pressure and temperature. Okay. So, you have basically two knobs, but also it becomes slightly more complex to tune the process and get the desired results. Okay, we'll stop with this. Now, if I want to deposit silicon by CVD process, right, there are different, you can get amorphous silicon, polycrystalline silicon, crystalline silicon, depending on what process conditions you use and also the what kind of substrate you have, okay. But if you look at this polycrystalline silicon, yeah, and this is an example that maybe will take a bit more time to explain. But in a VLSI older type technology, where you use polycrystalline silicon as the gate, you would really like this grains to be vertical, okay. So, there is some reason for this that we can discuss later on. So, columnar grains are preferred for better diffusion of dopants to the polysilicon silicon dioxide surface. So, we will discuss it in the next class. So, this can be obtained by controlling the nucleation initial phase of the growth, and this is a function of both temperature and pressure, yeah. So, you can control this very well, how the grains are formed and grow during the process, okay. And in APCVD, this is a difficult proposition, yeah. So, we will discuss this in the next lecture, yeah.